Hello everyone, and thank you for tuning into this talk. My name is Cameron Snow, and I'm one of the co-founders and the subsurface lead at Denomix. In this talk, I'm going to be discussing how to effectively manage and execute on MultiWell petrophysical projects. I'm giving this talk as part of SPWLA's The More You Know series. So before we jump into the talk, I wanted to give you a brief overview of what it is we do at Denomix. We're building out a collaborative cloud-based subsurface interpretation platform. This platform currently has 3 product lines available. So the centerpiece of this is our Petrophysics platform. We designed this to be natively multi-well so it can scale to projects with thousands of wells. While still giving you access to the workflows that you're familiar with. So this would be both deterministic and mineral inversion based workflows. And we use a lot of machine learning and automation to help you streamline your projects and execute on your analyses faster than ever before. We also have a production and economics package that allows you to do a combination of automated manual decline curve analysis, build out multi-well type curves, and perform rapid economic evaluations. Our geoscience package includes mapping and cross sections as well as strat column management. And in 2021, we're really focused on building out both a seismic viewer and interpretation capability. With respect to this talk, as I said, we are going to be talking about how you effectively manage and execute on multi-well petrophysical projects. So just to make sure we're all on the same page, I'm going to start off, what are the differences between single well and multi-well petrophysics. Then we're going to talk about data prep, as that's a big part of executing on these projects. Then we're going to talk about how you can evaluate parameters at scale, and then I'll finish up with a few tips and tricks. So when I talk about single well versus multi-well petrophysics, I want to make sure that we're on the same page here with what I'm discussing. So to start off, there are no real differences between single well and multi-well petrophysical projects, at least with respect to the methods and objectives that we use. We still want to identify and apply a workflow to these analyses, and we're doing this so that we can quantify our reservoir properties, we can evaluate the reservoir fluids, and at the end of the day, we want to create some high quality work product that has impact on our business. However, there are real differences with how we execute on the workflow. For example, we may have data from multiple vendors, multiple tool generations, etc. And this creates complications with respect to data management, perhaps the quality of the data or the scale of the data, and we'll need to address that. We'll also have a logistical challenge between managing, setting, and assigning parameters across hundreds to potentially thousands of wells. And we'll need to make sure that we are integrating regional knowledge. When we're looking at multi-well petrophysics, we need to take that spatial component into account. And at the end of the day, we are trying to create a high quality enough work product that we can create value at a meaningful scale to our business. Okay, with respect to single well petrophysics, this is what I like to refer to as the gold standard of analyses. We're focused on getting our data 100% accurate and ready to go. Then we want to manually establish every parameter very carefully, zone by zone, make sure that we are very well tied into our core and fluid data, really take advantage of those specialty logs like NMR and image logs to make sure we're getting a best-in-class analysis. And doing this can often take multiple days. So what do you do when your geologists or your engineers are coming to you asking for hundreds of these types of analyses? All too often, the answer is to go to bulk log calculations, and this is where you choose a very limited equation set. You often use all the wells have all the same parameters, and often even some of the zones have the same parameters. You apply this, and then at the end of the day, you get out a very generic answer. And I would say that this answer is often of uncertain value, especially if you want to apply it to more advanced problems. But, there's a whole spectrum in between these two end members, between this single well analysis versus this very cookie cutter bulk log calculation approach. There is a spectrum, and, where do you need to be on this spectrum to create the value that you want? Your single well interpretation, this is something that if you're working like a deepwater Gulf of Mexico well or a pilot well on a pad that lots of horizontal wells are going to be drilled off of, certainly you need to go through that gold standard analysis, and that's just driven by the amount of capital being spent. Maybe bulk log calculations are okay if you're looking, just doing some high-level scoping work, maybe trying to high-grade something very quickly. In between this, that is the domain of MultiWell petrophysics, and this should be something that can influence decisions anywhere from infill drilling through completions design, and that's what we're going to be talking about today. So with MultiWell petrophysics, we're still applying that best-in-class workflow. However, we are going to do some things a little bit differently. First of all, we are going to try to leverage automation to handle a lot of the data prep and conditioning. We're going to try and use statistics and spatial data like maps to inform our parameter selection at scale. We are then going to focus on that core and fluid calibration still. However, instead of using specialty logs, we're going to use the commonly available suite of logs because we want to be able to apply this to large numbers of wells. I'm going to advocate that we try to build up what I would call a key well petrophysical blueprint, and this may take us multiple days, but we can then apply this to a large number of wells, and so as we expand our analysis out, it really saves us a lot of time down the road. So with respect to these, just laying out a summary, they are very similar, but the differences are that we are going to try to automate the process and be more spatially informed and automatically set parameters in our multi-well petrophysical projects. And I will say that we will put more emphasis on QCing our results in a spatial way with the multi-well petrophysical projects. But at the end of the day, this is something that is not an either-or decision. One of the reasons you should be doing multi-well petrophysics is to create space for your petrophysical staff so that they can apply their expertise on those real value creative problems on those high capital wells. Okay, before you get started with a multi-well petrophysical analysis, there are a few prerequisites. First of all, you need to have a very well-defined stratigraphic framework, and you need to make decisions on what you're going to do when there are missing tops or when there are partial zones, because this will affect both the interpretation and the QC process after the fact. You need to understand what properties vary spatially across a play. We'll go into this in detail. And then I would argue that you also need to understand what it is your downstream users need to get out of the analysis. This will affect how detailed you are in the analysis, but it'll also affect perhaps what set or subset of wells you work in as the data requirements change. Okay, so once you've got those prerequisites out of the way, it's time to really focus on getting your data interpretation ready, so then you can start doing your calculations. So when I refer to interpretation ready data, this is the process of doing the data preconditioning, normalizing your data, identifying washout, and repairing that. And I like to put it in what I call my 4C framework, which is you want your data to be clear, consistent, complete, and clean. Okay, and we have to do this because of some of the challenges that log data presents us. So there are what I call structural problems, and these are things like curve mnemonics, the fact that we have multiple logging runs, we have differences in units and lithological references, and these are almost in a way self-inflicted wounds that we're going to be dealing with. And then there are the true subsurface problems where the data is misrepresented. And this can be caused by things like washout, it can be caused by poor digitization, it can also be caused by variations in tool response from vendor to vendor, from tool to tool. So the way I want to deal with this is by taking the two-track solution. The first track is going to deal with the data attributes. Those are the structural problems I talked about, things like curve aliasing, units, lithological references, and compositing. And the second track is going to be focused on data quality, so looking at inconsistencies in data scale that aren't driven by the subsurface, and also looking at washouts and how we deal with errant data. So with curve mnemonics and aliasing, you all know the nightmare that curve mnemonics can present, especially when you're working with hundreds to thousands of wells. We've done a bit of research at Denomix on this. We had a database of around 60,000 LAS files that we analyzed curve mnemonics on. And that led us to develop this chart that you're seeing here. And what this is showing is that if you have about 100 mnemonics in your alias table, you're going to capture about 50% of the available data. If you have 500 curve mnemonics in your alias table, you're going to capture about 75%. If you want to get to that 95 to 99% data capture rate, you're going to need somewhere between 5,000 and 10,000 curve mnemonics. So this is something that it takes a lot of upfront work, but once you get this done, it is well worth it. Okay, we also have units with, or issues with curve units and curve families. So with curve units, these can come in a variety of different things. Do we have, decimal versus percent, for example? And it can also, we have issues with curve units having their own mnemonics. For example, your density curve is in grams per centimeters cubed. Is that GCM3 or is it G per cc? Etc. So there are a lot of issues even with trying to read and understand curve mnemonics. And then we have differences in the way that curves are reported, even when it's the exact same tool. Do we have, for example, a density porosity or a bulk density? How well has, that been documented, that conversion from one to the other? Do we know what matrix density we need to use? Do we know what fluid density we need to use? And are we comfortable potentially with having a little bit of uncertainty around that? And, I would say that this is something where you need to have a internally developed workflow for getting all of your data in the same unit space and in the same curve type space, when we're dealing with the same curve families. And this expands out to lithological references as well for things like the neutron curve. So, that's another thing that needs to be addressed. Okay, so, I just went over a few of the examples there with curve aliasing and curve units. For curve compositing, this is getting, all your files from multiple runs, stitched together and spliced together. But once you have that done, then you should be clear, consistent, and complete with respect to your data. Then you still need to get it clean, and that's where the data quality track comes in. So first of all, let's talk about scale, and this is about log normalization. So when do you want to normalize? Well, you should absolutely normalize if you're a geoscientist and it helps you do your correlation. You should also normalize if you're trying to address problems caused by variations like tool generation or differences between vendors. When should you not normalize? Well, do not normalize if it results in losing geological information. If we start to wash out the subsurface response, normalization means that we are, degrading our petrophysical analysis. And remember, normalization is not a way to fix bad data. That is a separate step. And then when you're doing normalization, you need to think about the methods that you're applying. Are you shifting data? Are you doing a stretch and squeeze? Are you doing, a 3-point scaling operation? So there are a lot of different ways that you can go about this. You also need to think, what are you scaling relative to? Is it relative to a fixed range, relative to a key well, relative to a group of adjacent wells, etc. So this is an area where you need to put a lot of thought into the method, and you need to carefully QC the results. Okay, so when it comes to QCing the results, we need to look at this both in map view and in cross-section view. In cross-section view, we're mainly looking for the amount of stretching and squeezing that is gone on in our logs, how much have we shifted them, etc. In the mapping, I like to use this as a way to try and evaluate if we're normalizing out geology. For example, here in my before map, it looks like we have a few areas with a misrepresentatively low gamma ray response. You can normalize that out to get to a much smoother looking map post facto. But when you look at the scaling that was applied, what you see is that everything to the southeast has been shifted to lower values and everything to the northeast has been shifted to higher values. And that this happens to run subparallel to my depositional strike. And that's a good sign that we're normalizing out geology, which is not something we want to do, which means that we probably need to take a more measured approach and maybe even consider only normalizing over smaller subsets of wells. Okay, when it comes to dealing with washouts, this is normally a process where we identify, where we have a bad log response, recognize what curves are reliable, and then reconstruct the unreliable log responses. And if we don't do this, as you well know, we will end up overestimating the porosity. And that is why I believe it's crucial for us as petrophysicists to take care of this before we, pass off projects to any other downstream users. Okay, so a few thoughts here on bad hole identification. Although in a single well analysis, using the caliper log is a very common practice. When you're working with multi-well projects, I often encourage people to avoid using the caliper log by itself. And the reason why is because hole size can vary from well to well, with depths, they're not always going to use the same hole size, in the same interval. So, trying to set a fixed cutoff on the caliper log is often going to lead to misrepresenting what is good and bad data. So I often like to use some type of derivative of the caliper log, like a borehole rugosity. I also like to use density correction and actual cutoffs on the density curves. And then for repairing these, there's a number of ways you can go about repairing it. You could just null out the data, for example, and that certainly ensures that it won't get used, but it also means that you're losing some information. You could, change to a different method. However, if you're changing the method that you're using to evaluate your porosity, then you risk having apples to oranges interpretations. And so this is why I, encourage using some type of correlation. It could be something like a simple relationship, like the Gardner relationship, or it could be something more advanced, like, using a machine learning model to, to predict what the curve value should be over that washed out interval. Okay, and once we have done that, your data should have been preconditioned to have clear and consistent names, consistent units, consistent references, and have a complete data set. And then we have modified our data to have consistent data ranges via the normalization process. And then we have used, some technique to identify and repair data in washout intervals. So, we now have a clean data set as well. So how can Denomix help you in this area? Well, we have spent a lot of time focused on getting data interpretation ready, and this is because we deal almost exclusively with large data sets, large projects. We have a pre-built alias table in the background of over 7,500 curve mnemonics. We've also automated the workflow for unit checking and conversion. We've automated the workflows for converting over curves in the same tool family to a common reference. We do lithology standardization and curve compositing and splicing, all in the background, all automatically, so you don't have to deal with that. We've also added one-click curve normalization, so you can rapidly do that, as well as pre-built maps for QC, as well as pre-built cross-sections for QCing your normalization. With respect to repairing bad hole, we have automated this process via machine learning models. So you have access to things like multilinear regression and random forest to help you automatically reconstruct these curves across the washout intervals. And finally, we've built in some log health check tools, so that way, even before you get started, you'll have some type of indication of problem wells. So now we're going to move on to parameter evaluation and interpretation. So a lot of what we do as petrophysicists is expertly set parameters that are part of these specialist equations that we use. Well, in MultiWell petrophysics, we're doing this very much the same way, but we need to do it in a way that scales. The challenge comes in through the fact that many parameters vary spatially. So, for example, in this map that I'm showing here, we have production bubbles from the Eagleford trend, and we can see in the southern part of the play to the southwestern part of the play, we have much higher GORs than we have to the north-northeast of the play. And so if you were evaluating things like oil or gas in place, you would want to take this variation in GOR into your analysis. Likewise, this is reflective of changes in maturity, for example. So you would also want to make sure that you have your maturity models varying spatially if you're integrating those into your petrophysics. And and that is what is the crux of MultiWell petrophysics. And if you get this right, this is where MultiWell petrophysics really comes into its own. And this is what truly distinguishes MultiWell petrophysics from both single well analyses and from bulk log calculations. And I would argue that this is a process that scales up exceptionally well when you have tools that enable you to do it. So with respect to some methods for doing this, we're going to go over a few of these. Probably my favorite way to do this is what I call parameter extrapolation, and that is where you have a map of a property and you extract the value from the map at your well location. I like this because QC is inherently built in. You can look at the map and you can see if there are potential issues with it. Also, depending on the maps that you're integrating, it means that you're potentially pulling in data sets and interpretations made by other experts. For example, this is a map of maturity in the Powder River Basin delivered by my basin modeling team. And so, you're able to, pull in the very detailed work that they did to get that best-in-class answer for maturity in this case. Also, mapping allows you to take sparse interpretations and propagate those. If you only have a few data points, you can take advantage of the gridding methods like kriging or inverse distance to really try to give yourself, an answer that is, reflective of what's going on the subsurface. Okay, very similar to this is what I call parameter interpolation. And this is where we use local correlations to fill in the blanks. Okay, so let me explain this to you. So here in the diagram, we have shown in blue points that we have interpreted manually. And if we can assume that the behavior in between those points is defined by the boundary conditions, we can then triangulate a solution in between these. And so, for example, if we're going through and making an interpretation on a parameter, and we do this in half a dozen wells, we can then use those interpretations to inform the adjacent wells. The benefit of this is that, we increase the granularity every time we add another manual interpretation. The limitation of this is, of course, it means that we have to be confident that the values that we are interpolating do lie in between our in-member data points. Okay, in Denomix, there's something that we use called parameter remapping, and I like to say this is an algorithm that looks at the style in which you make your interpretation. So, the easiest way to think about this is looking at something like the gamma ray, and what you do here is, if you look at this well log or you look at this histogram, when you pick your gamma ray clean and clay parameters, for example, you're picking them, somewhere on or off of the statistical distribution. And with parameter remapping, we measure a number of statistics. We then map your parameter picks to that statistical distribution. And then when you move to a subsequent well, we remap the parameters in that target well. So the best way to think about this is to look at an example. So here I have two wells. The well on my left is the one I interpreted. The well on the right is the one that was automatically interpreted via this parameter remapping process. And what I see, for example, is when I look at the Eagleford Shale, I have my clean and clay points at 55 and 206 in the well that I interpreted. In my target well, it has reinterpreted those as 57 and 200. This is helping deal with some of the minor variations in things like tool response that that are present in our large-scale data sets. And really the way to think about this is it's just the flip side of curve normalization. So instead of changing the data distribution, now we're changing our parameter interpretations. Okay, another area where I have seen a lot of promise is with conditional parameters. And what this is, it's when you set a parameter based on the value of another curve. Now, this could either be some type of correlation or regression, or it could be something that is very much like an if-then statement. So if your facies is equal to 0, then set your row matrix at 2.71. If your facies is equal to 1, set it at 2.87, and so on and so on. This can work well if you have a high level of confidence on your input logs and there is a strong correlation between those logs and the parameter that you're trying to set. So it can work very well, but the one thing I will caution is that it can become very prescriptive, especially if you're dealing with categorical data like facies. If you have 10 facies, you then have to have 10 if statements. If you go through and you add another facies group, so you have 11 or 12, then you have to go through and redo this. So it can become a bit cumbersome to manage. So a lot of thought needs to go into the input logs into this process. Okay, so how can Denomix help you with this? We built our platform to be natively MultiWell, and that means we have loaded it up with MultiWell petrophysical tools. So we have these petrophysical blueprints and zone definitions that help you manage parameters. We allow you to pull in parameters from grids or build them up, to interpolate between data points from scratch. We have our proprietary parameter remapping algorithms, as well as we give users full access to the back end, so you can define parameters as you see fit if you want to use something like conditional assignments there. Okay, so one of the questions when it comes to doing multi-well petrophysics is a question of whether or not to invert or not to invert for mineralogy. And so this is a question of methodology here, and I would say that when we think about mineral inversion, it offers a lot of upside on quality. It gives us this superior porosity result because we're calculating this running grain density curve. As we all know, it handles complex and mixed lithology systems better because we're no longer setting some parameters on a zone basis. We're doing this at every depth step. I think it's just a better way to go. And so, I've made that a core part of my workflow. And I think it works very well on regional scale projects. However, this can create a problem for you because I know a lot of geoscientists don't have access to software that can do this. Their mapping packages don't allow them to execute on this type of a workflow. And for those of you working with traditional petrophysics softwares, they just can't handle large numbers of wells, especially when you're running a full mineral inversion. So there are considerations there. However, I personally believe that the uplift that you get in the quality of your interpretation mandates doing this. Okay, when you're doing a regional scale mineral inversion, there are a few things that you need to understand. First of all, what is your minimum viable log suite? So, what I like to do is find a well that has a full suite of logs and see what happens if I turn off the sonic log, or if I turn off the PE log, or if I turn off both of them. How much does my answer change? And this is important to understand so you can quantify uncertainty in your analysis. You need to understand where there's that spatial variation in your model, so we can then map those parameters in. So, for example, clays are often something where we see a lot of spatial variation. Your sonic value of clay or your resistivity of clay may vary extensively across a play, and so you need to account for that. Same thing with fluid properties. You also need to understand where there are material changes. Although mineral inversions work very well at the regional scale, and this is due to the fact that, even though you may have facies changes, as you move from, let's say, a near shore to a shallow offshore to a deeper water environment, you still have the same mineralogy, so you can still apply the same mineral model. However, sometimes you hit hard boundaries. Like, for example, when you go from the Delaware Basin to the Central Basin platform back to the Midland Basin, that is such a material change that you are going to have to change models and split up your project. So you need to be aware when there are those material changes. And you also need to have a strategy for QCing this. I like to do the QC process via maps of things like grain density, maps of mineral volumes, and looking at things like my model error, mapping that up and figuring out, are there specific areas or of specific zones where I have more model misfit than in other areas. Okay, so when it comes to mineral inversion, I said that maybe a lot of you would struggle with this because, either you're a geoscientist and you don't have access to tools that can perform mineral inversion, or as a petrophysicist, your software tools don't allow you to do this at scale. Well, that's one of the problems that I really think we have cracked at Denomix. We have what I would say is the fastest mineral inversion package on the market. It's 30 to 50 times faster than our competitors' solutions. We've tested it for accuracy against several other packages, and it's always came in as expected. We have tried to put together a nice, clean, simple user interface for building out models zone by zone, and we focus on making sure that it does real-time updates. So as you start changing parameters, changing your mineral mix, etc., you're seeing the results in real time. Okay, so I just want to wrap up with a few tips and tricks to help you along through these multi-well analyses. So when it comes to doing multi-well petrophysics, an effective QC of your results is absolutely key. And once again, this is something where you may have problems with the current tools that you're using. So often geoscience tools are better for QCing our results. So for example, one of the most powerful ways to QC your results are to look at maps. And this is because we want to make sure that we have that spatial context correct, and we want to see, are there trends coming out in our data that make sense. So first of all, you need to be comfortable getting in there into your mapping package and doing this. And you need to start early in the process. You need to, not only QC at the raw log stage, But then you need to do it after each step in the interpretation workflow. You do your normalization, you QC it. You do your clay volume, you do another QC. And by doing this QC process along the way, as opposed to trying to do it all at the end, each module that you run, each step of the interpretation will be a little bit faster. I would also encourage you to map out your parameter values as well. I think this is important because a lot of times you can get a nice looking map at the end, but then when you turn around and you start looking at the parameters used to generate that map, they may not make sense. And so I think it's important to map out these parameters. And I would encourage you to do this if you're working in a single well basis to see if your interpretations are really holding up in a spatial sense. And make sure to do this zone by zone. It's key to look at this from top to bottom to see are there any wild inconsistencies as you go through these. Another effective way to QC results is through cross sections. So once again, it's another geoscience tool that you as the petrophysicist may not have access to in your traditional petrophysics package. The reason I like cross sections is they put everything in the context of depth, and they can help us either feel more certain about what we're seeing with our mapped out results, or they can explain why we may be seeing some variations in our maps. Some tips here. Remember, we're doing this to highlight problems and to try and find issues in our interpretation. So feel free to change your scales and highlighting to make sure that you can understand where you have problems. For example, if you're QCing a porosity interpretation, maybe you use specific shading to highlight exceptionally high porosity values, so your eye is really drawn to those wells. And cross sections will also highlight any problems that are related to your framework, or to not doing some of that definition work up front with respect to poorly defined or partial zones. So what do I mean by this? Well, if we look at this example well that's called out, we have a missing top here. So if you're comparing, these two wells, or these three wells here, and the middle well is coming up somewhat different, how much of that is driven by, having inconsistent stratigraphic definitions? Or perhaps if you were looking at a map of TOC in the Eagleford Shale, which is shown down here at the bottom, and maybe you saw a low value in this well. Well, that could be explained by the fact that we only partially logged this zone, and we don't have logs over the TOC rich portion of the interval. And so, looking at cross sections can help put your maps in the correct depth context, and can help you understand why there are some variations. So how can Denomix help on this front? We are a fully integrated geoscience and petrophysics and reservoir engineering package. This means you can map your results in the platform. This saves you a lot of time. There's no need to export out, then re-upload that to your geology package, have your geologist, build and look at those maps, and then, come back to you with potential changes. You can now do that QC in the platform. We also have cross sections, tops picking, and zone management, so you can go in, define those petrophysical zones, define what happens when you only have partial well logs over a zone, or missing or inconsistent tops, and you can go in and you can update that framework without having to go back to your geologist there. And having all this in the same platform, combined with a fastest on market mineral inversion package, means that you're going to be able to start iterating faster on these projects. You're going to be able to test more scenarios, and that's going to help you get a better answer. Okay, so just to wrap up and summarize some of what we talked about, remember the methods and the objectives and the knowledge base that you apply in executing on a multi-well petrophysical project is no different than what you will be doing on a single well petrophysical analysis. The real difference comes in using these specific techniques to pull in knowledge from spatial data sets, things like maps and offset interpretations, so you can ensure that each well gets its own custom interpretation instead of using some cookie cutter type of bulk log analysis. This is something that we focused on a lot at Denomix, and hopefully this is something that we can help you use to take your organization to the next level when looking at these big projects. Thank you for your attention. I really appreciate it. If you have any questions, you can always reach out to me at csnow@denomics.com. Thank you.